Hello and welcome to this GLEON organized workshop on toxic cyanobacteria risk assessment according to the guidelines from the World Health Organization. My name is Bas Ibelings and I work at the University of Geneva in Switzerland. The book we will follow for today's presentation is shown here, the WHO, World Health Organization Handbook Toxic Cyanobacteria in Water, a guide to their public health consequences, monitoring and management. And you can see pictures of the two editors of this book, Ingrid Kores and Martin Welker. You can also see the link where you can freely download this book and read it if you wish to do so. Here's a slight overview of the content of the book. In the book, we move from understanding the hazard, an introduction to cyanotoxins, and an introduction to their producers, the cyanobacteria. Then we move on to preventing hazardous exposure to cyanotoxins in drinking water, recreation, food, renal dialysis, and dietary supplements. Next is monitoring cyanobacteria and cyanotoxins, and finally, public surveillance, communication, and participation. And as said, you can all read this in the freely downloadable book. The book is authored by quite a few researchers from the field. This is just one of the chapters I show here. I was asked to take the lead in a couple of chapters, and this is a chapter on understanding the occurrence of cyanobacteria and cyanotoxins. You can see the co-authors on this particular chapter, and you can see the content where we discuss cyanobacteria, their key traits, their functioning, and why they particularly cause problems under more eutrophic conditions. Those of you that have joined us from the US, in particular from the Great Lakes area, you may well be aware of this example. This is a bloom in the western part of Lake Erie, toxic cyanobacteria, and at some point the mayor of Toledo decided to close the tap water system. Why? Because there was microcystin. Microcystin is the most widespread, best studied of the cyanobacterial toxins, in particular microcystin LR, one of the many different variants. And the concentration of microcystin in the drinking water, so in the final product coming from the tap, exceeded the WHO guideline value of 1 microgram per liter of microcystin LR. And for that reason, the mayor decided to close the tap water system and bring in drinking water via bottles. You can imagine that's a huge undertaking. If you follow this workshop, I hope that you'll understand and maybe you agree or disagree with me that scientifically the mayor did not need to close the tap water system despite the value of microcystin exceeding the guideline value of 1 microgram per liter. I'll try to explain why I think that the tap water system could have remained open. I also understand that for a mayor with different responsibilities than strictly scientific ones, the decision may well be different from those that you would take purely on scientific reasoning. Just one slide to say I got involved in work on toxic cyanobacteria, not first of all because of the risks for humans, but because of the risks for the ecosystem. So this is a paper we published on microcystins in the lake food web. That's a lake in the Netherlands where at that time there were a number of years with massive fish kills, also bird kills. And we asked the question, the fact that those kills coincide with development of big blooms of toxin-producing cyanobacteria, does it mean that the blooms are responsible for the death of the fish and the waterfowl? You can see in the title that we found no evidence for biomagnification, which would be typically found for substances like PCB that are fat-soluble. Microcystins are more water-soluble, meaning actually that we see here that with every step up in the food web, microcystins go down, so biodilution rather than biomagnification. This led us to conclude that the likelihood that the microcystins are directly responsible for the death of the fish is not very high, And since the fish don't eat phytoplankton directly, the toxins must have reached them via the food web, and for that reason it's important to note that there's no evidence for biomagnification where they would increase with every step in the trophic structure. Later on, in particular working with Ingrid, I started to become interested in the risks for humans. What you can see in this paper that we published in 2014, we compare guideline values between different countries on different continents. And on the left, the black bars, you can see that the guideline value used to decide safe levels of microcystin in drinking water doesn't vary very much. It's based on the same derivation of the guideline value that we will go through. Based on the same scientific evidence, different countries arrive more or less at this 1 microgram per liter. On the right, however, you can see a 3-tier alert level framework for recreation. So in white bars would be low risks, in black bars moderate risks, and in the more hatched pattern the risks go up to the highest level, alert level 3, which in many countries would lead authorities to close the lake for recreation. Just by looking at the height of the bars for the different countries, you can see countries arrived at very different levels for their alert level system. And in the paper we discuss why that might be so. Basically, one factor that plays a role is that in different countries you have different leading scientists on the topic, and they may differ in their interpretation of the information that's available in the scientific literature. So now follow 3 slides. I will not read out those slides to you because I go through them later on. But if you want, in the book you can go to this box and see how important elements like here, the TDI, the tolerable daily intake, are defined. Then the box continues with things like NOAL and LOAL. And NOAL is the no observable adverse effect level. The dose of, in this case, still microcystin, the best studied and first studied of the cyanobacterial toxins. The NOAL, where in animal studies there were no adverse effects found at that microcystin dose. And then the box continues with the important notion of uncertainty factors in the derivation of the guideline values. And we go through that in the next slide. So here schematically you can see how the tolerable daily intake of cyanobacterial toxins and the guideline values that are derived from those, how we obtain them. Typically, you need what is known as a pivotal study. Ideally, from a human safety point of view, you would use exposure data, dose response data that are directly obtained from human studies, because then the uncertainty in your data is a lot less than if you use animal models. You can understand in particular in an experimental setting that is not possible, and that's why in most cases, in particular true for the cyanobacterial toxins, the guideline values are based on animal model studies. Now, the question whether we should be using animals to derive guidelines, safety values for humans, that's a valid question to discuss, but I'm not going to go into that today. There's a whole development to try to minimize the use of animals in toxicity studies. So here you take animals, an animal model system, often mice or rats, and you do an experiment where you inject, for instance, the animal's IP injection into the belly with different dose of the substance of interest here, first of all, microcystin LR. In this range of different dosages, you find the dose that in your animal system has no effects at all, no harmful effects. That's the NOAL, not in the behavior, not in the tissue, and so on. Then the next line, we have to introduce 3 uncertainty factors, each one of a factor 10. Why? Well, first of all, There's uncertainty because we base ourselves here on a know-how obtained from an animal study. We're a different species, we're not mice, we're not rats, so that's an uncertainty factor of 10 introduced. You divide the know-how by 10 to make it 10 times more strict. The next one is uncertainty between humans itself. They vary in their sensitivity, so that's another factor 10. So now we divide by 100. And then finally, there's different uncertainties in the data. For instance, are microcystins carcinogenic? We still don't know for sure. And also, you extrapolate from an animal study that took maybe 6 or 10 weeks, and you extrapolate in this case to a TDI, which is a tolerable daily intake for life, day in, day out for the rest of your life. So there's uncertainty in that extrapolation from short-term exposure in the experimental study to lifetime exposure via drinking water. So this is how you arrive at the TDI, the know-how from the animal model divided by 1000 in this case, 3 times factor 10. And then the guideline value is the TDI multiplied by the body weight multiplied by P, which is the proportion of microcystin that we say can be attributed to drinking water, as opposed to other exposure routes like food or recreation, for instance. And we divide by C, which is the volume of drinking water taken in typically by an adult person per day. And the exact numbers of this box, I'll give them to you in a minute. So here's one of those pivotal studies that were used to obtain the know-how. You can see in this table the know-how and the low-how indicated in red. So with this mice study, which in fact was not IP injection but cavage, so feeding of the microcystin, you can see that in this mouse study, the know-how that was obtained was 40 micrograms per kilogram body weight per day. So at that level, at that dose, there were no adverse effects in the mice. The low-how is a bit higher at 200 microgram per kilogram body weight per day. There are some small harmful effects observable. So this study by Fawa et al., and there's just 1 or 2 other studies, led to the famous 0.04 microgram per kilogram per day tolerable daily intake for lifetime exposure in the red box. That's the TDI derived as shown in the previous couple of slides, 0.04 microgram per kilogram per day. In this paper with Ingrid Chorus, we started to question whether it makes sense to always base ourselves on lifetime exposure. This was a review where we reviewed the evidence for cyanobacterial toxins in freshwater seafood, in fish or crayfish, or in some countries snails. And we say, how likely is it that people are exposed to microcystins or other toxins through their food day in, day out for the rest of their life? We say it's more a seasonal exposure, maybe during a summer season or so, where you have blooms, where you harvest shellfish or whatever, and you eat that for a few months or a few weeks at most. And for that reason, here, for the seasonal TDI in the middle of the table, we say we can take out one uncertainty factor of 10 because the extrapolation from a short-term experiment of, say, 10 weeks to lifetime exposure is not needed here because it's a short-term intake anyway. And then taking uncertainty of 100, the TDI is 0.4 instead of 0.04. And then there could be an acute intake of microcystins. For instance, if you go swimming and you swallow, say, some blue material, the acute TI would be 2.5 instead of the original 0.04. So here we start to differentiate between, say, different types of exposure, and that becomes relevant for the rest of the slides. So to repeat, here is the derivation of the provisional TDI for microcystin LR, one of, say, 250 different variants of microcystins, know-how divided by uncertainty factors, 40 divided by 1000, leading to the 0.04 microgram per kilogram per day. The guideline value, I promise you the numbers that were used to get to the guideline value. You can see the same formula we've seen in the box. The NOAA is 40, the body weight is taken worldwide average of 60. Some countries take an average body weight that's a bit higher. The P, the proportion attributable to drinking water, is 0.8, uncertainty 1000, and 2 liters of drinking water per day, leading to a value of 0.96, which is roughly the 1 microgram per liter, which is the guideline value for lifetime exposure, here indicated as the guideline value for chronic exposure that has been in use for quite a few years now. Then the book continues. As just discussed, there's not always lifetime exposure. Sometimes there's just maybe a few days, at best, a couple of weeks, where microcystin values would exceed guideline values, or where microcystin is actually detectable in drinking water. So here is the derivation for a short-term guideline value for microcystin in drinking water. So the P is now taken as 1.0 instead of 0.8. So we say for this brief period, all of the microcystin exposure comes from drinking water. But importantly, the uncertainty factor is not 1000 anymore, but 100, leading to a guideline value for short-term exposure of 12. So then back to the question of Toledo, the mayor closed the tap system because the microcystin concentration, I think, was in the order of 1.2 microgram per liter, exceeding the guideline value for chronic exposure, but it was only there for a few days. So clearly 1.2 is well below this guideline value for short-term exposure. So maybe, again, scientifically, we can conclude that the reason why Toledo, Ohio couldn't drink the tap water, we changed it to they could have taken tap water because it was short-term exposure. Along similar lines, you can derive a guideline value for exposure through recreation, like swimming or surfing or canoeing. Same formula, the NOAA of 40, body weight in this case, the body weight is taken as 15 kilograms because it's considered that it's more likely that children are exposed to microcystins through recreation than adults, so 15 kilograms. In the picture from Jora Tolman in the Netherlands, you can actually see how kids have dug canals in the beach and let this nice green stuff float in. You can easily imagine how it could be on their fingers and they might be exposed to it. So 15 for a kid. Uncertainty factor, again, 100 because it's short-term rather than lifetime. And the C, the intake in this case, is taken as 250 milliliters. Based on the literature, when people go swimming, this is a fairly typical volume of water ingested, leading to a guideline value for recreation of 24. We've said from the beginning that there's other cyanobacterial toxins than the microcystins. So the microcystins, we've seen the numbers in this table, the 1, 12, and 24. You can also see when data are available for other toxins like cylindrospermopsin and for the neurotoxins anatoxin A and saxitoxin, how lifetime, chronic, short-term, and recreational guideline values, how they play out based on, again, animal studies available through the literature. So short-term values, we say here, exceedance of guideline for 2 weeks once in a season. And the guideline value can be applied to the sum of all different congeners like microcystin. There's many of them. If you have different congeners, you take the sum and you apply the guideline value to the sum of the different congeners of that toxin. Then there's other toxins and metabolites for which there are no guideline values. maybe we should say not yet in the book, including anatoxin AS and dermatotoxins. Also specific case leading to long discussions when we were preparing the book. What about BMAA? Maybe you know about BMAA. It's a substance produced by cyanobacteria that is in the literature linked to neurodegenerative diseases like ALS and Parkinson or Alzheimer. The specialists among the authors of this book decided that there's no convincing evidence for the role of BMAA as a cause of neurodegenerative disease under realistic exposure scenarios. So it's not in the book. Some consideration about what does this mean? How should we interpret the risk of, say, microcystins, other toxins in drinking water when you go swimming in a lake? How does it compare to other risks, in particular other risks linked to water? Because that's what we talk about here. So what is a risk? A risk is defined as the likelihood of something occurring multiplied by the severity of the consequences if it occurs. So you can see on the y-axis of this table the frequency with which certain events occur from very often, like taste and odor problems in drinking water, which are bad for taste and odor, but not necessarily bad for your health, to occasional to rarely. And on the top, the severity of the public health impact. Again, taste and odor, frequent but minor impact. Cyanotoxins in the drinking water, in particular, if it's for life, they're worldwide, maybe we should say quite frequent, but with moderate impacts on the health, in particular if you stick to the guideline values clearly. And something that happens often and has major health impacts would be microbial contamination of drinking water, which is the case. Many countries do not have access to safe drinking water, and that is typically because of microbial, say, fecal pollution of drinking water. So this is a box that helps you to put things into perspective. Cyanotoxins are an issue, a health issue, but maybe not the most serious of the drinking water health risks that many countries face. So in the context of toxic cyanobacteria, in the context of, say, thinking about this in a WHO context, what makes them special? Cyanotoxins are among the most toxic naturally occurring compounds, that's true. LD50 is quite low for many of those compounds. There's widespread occurrence that may be difficult to avoid, because if your drinking water comes from a lake or a reservoir where you live, there may not be an alternative source. Maybe there's less public awareness of those risks than for other chemicals. I think that depends very much which country you are. And the control of cyanobacteria and the toxins can be indirect and complex. We have a little bit of that at the end of this work. Maybe similar to other chemicals in water, talking about the context of toxic cyanobacteria, there's a lack of quantitative data, dose estimates for human exposure. The contribution of toxic chemicals in water to morbidity and mortality is rarely acute, so you need a long-term vision. And it's often unclear whether cyanobacterial toxins were really the cause of symptoms reported. Imagine you go swimming, in the evening you don't feel well, you're nauseous, you're vomiting, you report this to your doctor. Was this really because of toxins produced by cyanobacteria in the lake, or maybe because of other microbes like linked to fecal pollution? Not often very easy to make that distinction. So far we've spoken about drinking water as an exposure route and recreational exposure. Other than that, there's potentially, like mentioned actually, food exposure. There could be, take the example of the dialysis clinic in Brazil, renal dialysis, where dozens of people died after being exposed to microcystins via water used for the dialysis. And there's an increasing use of dietary supplements, health pills, and there we need more good data to see what are the risks of those often dried cyanobacteria. Microcystins have been found in them, but we need more data. So the newly derived guideline values you can find in the book. Guideline values are applied to total microcystins, total cylindrospermopsins, and cyanotoxins. Allocation factors typically taken 80% for lifetime exposure to drinking water, 100% for short-term exposure or recreational exposure. So the allocation factor depends on local settings and depending on the activity, and you need to be aware of that if you develop local guidelines. Food or recreation normally is taken only as 20% allocation, but again, adapt to local circumstances and be mindful of other health effects. Water intake, 2 liters for drinking water, to have 250 ml for a child being exposed through recreation. And you can see the uncertainty factors as discussed for lifetime, short-term, and recreational exposure. In this case, not only for microcystin, but also for cylindrospermopsin and cyanotoxin. So both for drinking water and for recreational exposure, we use an alert level framework to help you to understand what are the risks in the setting where I am, where I may be responsible for taking decisions, and that's the alert level framework. It's a monitoring and management action sequence, a decision tree, which can be used to provide a rapid response to a cyanobacterial bloom. So clearly here, always adapt to local conditions where you are. Parameters used to trigger alerts could be visual, like turbidity, Secchi discs, microscopic use, where you can obtain things like cyanobacterial biovolume or chlorophyll, in particular if you're able to do cyanobacterial chlorophyll numbers. It's not the biovolume, it's not the chlorophyll directly that you're worried about. You're worried about toxins, but if you often enough calibrate, say, cyanobacterial biovolume that you can obtain from the microscope against toxins, you can use biovolume as an indicator of the risk of being exposed to the toxins. And toxin to biomass ratios can vary not only between water bodies, but also between months, between years, within the same water body. And on the right, you can see different lines for different lakes in Germany go up and down between different years. So it's variable, and that doesn't help in making easy decisions. This is a busy slide. I will not go into detail. It's just you can find it again in the book. It's to say that efforts have been made to link indicators of cyanobacteria, like their biovolume, for instance, to the kind of level of cyanobacterial toxins that this biovolume may represent. So as you can see in the table, if you have low biovolume, in this case 0.3 millimeter cube per liter cyanobacterial biovolume that you obtain from the microscope, that would correspond to, say, 1 microgram per liter of microcystins. If you go up in the alert level system, go up to the next level, level 2, to 4 millimeter cube, and above that even 8 millimeter cube, you can see how that starts to correspond to high levels of microcystins. So this is how, even if you don't do frequent, say, weekly measurements of cyanobacterial toxins, but you're able to do microscopy, you can still get fairly reliable estimates of the risks that you're dealing with. And that is written in this red box. If these alert levels for biovolume are not exceeded, the corresponding microcystin concentrations are unlikely to exceed the guideline values. And this is because those biovolume levels are a fairly conservative approach. Then here is what an alert level framework, for this case, drinking water supply, would look like in reality. That is printed in the book. At the top, this is where you begin. So somehow you have an indication that in your reservoir, for instance, there's a risk of cyanobacteria and their toxins developing. It could be from a Secchi disc reading that is decreasing. It could be from direct observation of maybe surface blooms or taste and odor. The various things you would start to do, one is to do microscopic examination, and there you could see if potentially toxic cyanobacteria genera that are known to be toxin producers are present. If that's the case, you scale up to vigilance level, which is the basic level in your alert level framework. Then you would need to do weekly determination of cyanobacterial biomass and regular inspection of the offtake for the production of drinking water. Then if in your microscopic or otherwise examination, you start to exceed a certain threshold, like the 0.3 millimeter cube biovolume, or here 1 microgram of chlorophyll A with dominance of cyanobacteria in your lake reservoir, you scale up to the next alert level 1. Then there are various actions you would need to take at level 1. Consult with the local health authorities, inform sensitive groups, consider implementation of contingency plans, including use of advanced treatment or alternative water supplies. You continue to do microscopic examination of the water. If you then start to exceed the next level, which is here 4 millimeter cubed or 12 micrograms of chlorophyll, you scale up to level 2, which is an elevated risk to human health. And then the actions you would need to take are following up from the actions we've just mentioned. But again, communication with authorities, health authorities, and so on, with the public is still key. So that's how an alert level framework for drinking water would look like in reality. You can see on the side of the various slides that at any moment, of course, you can, if you have the means like an LCMS or so, or sometimes simpler means like ELISAs, do measurements of the cyanobacterial toxins so that for your system at that time, you can link biomass to toxin levels. One graph that comes from the book, and like shouted out here, it's alive. And that is different for cyanobacterial toxins than for most other chemicals being produced by microbes, the cyanobacteria. You can see here since last cell count on the x-axis, how in just 10, 20 days, one or couple of weeks, you can move up from alert level 1 to alert level 2. You can see those are the horizontal lines in the graph, and how fast you go from one alert level to the next depends, of course, on how fast your cyanobacteria are growing. So it depends on the conditions, resources available, loss factors in your system that determines how fast biomass and therefore toxin concentrations increase. But this is a graph that highlights why cyanobacterial toxins are tricky to manage because it's so dynamic. Exposure to food, I'm not going to say too much. The basic science, the guideline values and so on are not any different. It really depends on local circumstances, local traditions, whether people may or may not be exposed to cyanobacterial toxins in freshwater seafood. One problem we highlight here, and that comes up in the chapter in the book, that if you start to measure toxins analytically, it becomes more complex to do this in animal tissue than directly in the water, in the phytoplankton. And therefore, that's one of the reasons that there's not all that many reliable studies, and that adds to the uncertainty surrounding what is the potential exposure to microcystins or the cyanobacterial toxins through food. Moving from food to recreation, here you can see warning signs that you may have seen at your local lake in your own language. You can see from the languages that these problems occur worldwide. Water managers are aware of this, and they use different means to communicate the risks, be it in permanent signs or in signs like on the top right that actually vary depending on the conditions at that time. The arrow may indicate if you move from low to moderate to high risk and so on. But it's a common problem. Recreation, it's another level of complexity to understand what are the real risks, because what you need here is epidemiological data. So you need to do a good study where you interview people that have been to a swimming location where there were blooms present, and you want to know, did people get sick or not from being in that lake? Not easy to do that correctly, to exclude other potential risk factors. There's very few studies available. So again, what we use from the literature, it's not extensive, but it's the best we have available in terms of epidemiology to extrapolate from blooms being present to certain symptoms that people report to the doctors, to the health authorities. This is a checklist. Again, no need to go through it in detail. You can see the gray arrow indicates the appropriate intensity of monitoring and intervention. At the top, the necessity to do so is high because there's almost daily exposure during the bloom season, for instance, at lakeside holiday homes. And there's a large number of people that use such a site for recreation. Then it's really important that you have proper, frequent, and high quality monitoring. The need for that goes down clearly for lakes or reservoirs or swimming sites that are not used as intensively. You still want to protect those people, but the need to do high frequently monitoring becomes less so, and it also depends on to what extent the users, maybe they're workers, that work on a particular reservoir, that would be well informed. Again, they know themselves what to avoid, what to do, how to avoid exposure, and then it all changes what you as a responsible authority need or need not doing. A similar alert level framework for recreational waters. The basics are the same. You need to be well informed of cyanobacteria, the dynamics in the system. So it starts again with things like, well, here you can see microscopy, or even simpler ways, keep track of transparency. Even if you want to start with very simple means, take into account the phosphorus level of the system where you are, because clearly the risks for exposure would increase if you go to more eutrophic systems. So on the left in the middle, you can see fairly clear water, slightly turbid, greenish discoloration, but Secchi disk between 1 and 2 meters. That would be the lowest level, the vigilance level, and that corresponds to microscopy values like we've just seen, biovolume between 1 to 4, 3 to 12 micrograms per liter chlorophyll A with dominance of cyanobacteria. If you want to know more, you start to assess characteristics, determining potential to support blooms or scums in your system, assess for cyanobacteria known to be toxin producers using the microscope or maybe genetic tools. If there are additional reasons to say, I can see, for instance, known toxin producers, you intensify your monitoring, you start to inform lake users, and you inform relevant authorities. And then, as before, if the values that you're following, like biovolume, like chlorophyll, maybe even toxin concentrations, start to exceed certain threshold levels, you scale up to alert level 1 and finally alert level 2. And you can see the kind of actions that follow from alert level 1: watch for scums, investigate further, inform site users, inform health authorities. We've seen that. Alert level 2: immediate action to prevent contact with scums, inform site users, authorities, and so on, and follow-up investigation by the public health authorities. Why do I bring up the word scum separately? We'll see that in the next slide. A scum is when floating cyanobacteria that have their buoyancy, their gas vesicles, they float to the surface. Maybe a light wind would even transport them to the shore. If this shoreline happens to be where you have your beach, you may get a very dense concentration of cyanobacteria right where people enter the water. And therefore the presence of scums, as we'll see later, because biomass goes up quite importantly, and most of those toxins are intracellular. The microcystins, the cyanotoxins, are intracellular, so if biomass goes up in a scum, toxin concentrations goes up. And that is why you need to be extra careful with scums, and that's why presence of scums, in particular thick scums, quickly lead you to alert level 2. So here are a few pictures that we make available. Scums come in different degrees. So on the left, more light level scums, level 1, and on the right you can see this would happen if the scums, from the open water, as you can see more in the pictures on the left, if the scums are driven by light winds to the shore where they accumulate. You can see where the swan is swimming. That's a twofold concentration vertically from floating cyanobacteria in the absence of wind that come to the surface, and then a light wind, second concentration horizontally, blow the scums onto the beach, onto the shoreline. And those kind of images, again, they play a role in your alert level framework. What I've just explained can be shown here. If you go from A to B to C to D, you can see A, the cyanobacteria are nicely suspended. The wind is blowing. They're suspended by turbulence by mixing in the water column. Maybe we have 10 to the 7th cyanobacterial cells per liter of water. Microcystin is 1 microgram per liter. Risk level is low. Then the wind drops. They start to float to the surface. How fast they float depends on their size. Like microcystins would be very fast floater. Planktotrix a lot slower. The number of cells goes up because now you're concentrating yourself in a near surface mixed layer. The cells go up, therefore microcystin concentration go up, in this case maybe 10, and the risk level goes up to moderate. If they continue to float up, so it stays calm, the scum at the surface just get thicker, maybe 10 to the 9th cells per liter. Microcystin maybe up to 100, risk level is high. And then in D, the secondary concentration, the horizontal concentration by a light wind, then you get to extreme levels up to maybe 10 to the 12 cells per liter, and microcystins levels up to very high concentrations, up to milligrams almost, and of course a very high risk level. So that's, at least for recreation, panel D is the highest risk scenario you could imagine. So speaking about the risks of recreation, and thinking back to the slide, the graph I showed, how different countries made very individual decisions on where to scale up in their alert level framework from alert level 1, say vigilance level, to 1 and to 2. Very individual decisions when to warn people, when to even close lakes. Some countries are very strict, like for instance New Zealand or California. Other countries, like Germany or here the Netherlands, are a bit more lenient. And here we try to explain that it's not to say that those countries that are not as strict are being irresponsible. It's just situations differ between countries, and as authorities you need to take more into account than just the health risk of cyanobacteria. So if we go through this text that comes from this paper, setting the alert levels in the Netherlands is the outcome of intensive discussions between scientists, lake managers and policymakers in a country known for the highly eutrophic state of its lakes, where stricter alert levels might result in an extended closure of many lakes for most of the summer. Safety, protection against cyanotoxins clearly must come first, but the protocol used in the Netherlands, in addition to health risks, takes into account the promotion of outdoor activities, in itself healthy, feasibility, complexity, and the costs of monitoring or risk control of cyanobacteria, as well as the ease of communication to the public. Given what we've seen with the uncertainty factors of 1000, given the large uncertainty in the derivation of the TDI for cyanotoxins, it's not even possible to say whether the higher alert levels used in the Netherlands truly represent decreased protection or insufficient protection of the public. We merely can say it's uncertain because it remains well in this range of 1000. Of course, the 1000 is there for a reason, but this is the very large uncertainty we deal with. And again, authorities have to take other factors into account, like during a heat wave, there's also a risk to ban people from going swimming and bringing down their temperature. So it's very much a local setting. And just to add one more factor to what we've just seen, that cyanobacteria may be distributed differently in a lake, from fully mixed in column A going to dense scums in D, or in a methylymnatic deep chlorophyll maximum in E, which is typically what we have in the peri-alpine lakes, typically Planctotrix rubescens. If it stays there, unless you're a scuba diver, people that go swimming at the surface of the lake, they're not much of a risk. But it's still, sometimes they come to the surface, so it's still something to monitor. In G, we're not going to go into much detail, but it is very much an upcoming problem. In G are benthic mats of cyanobacteria. And why is this deserving special attention? These are, for instance, headlines from newspapers where I work in Geneva. These are headlines about dogs dying in Lake Neuchâtel, which is not so far from Geneva. You can see in the circle a policeman holding up the responsible cyanobacteria, and it's not a planktonic cyanobacterium, it's a benthic mat. And like a scum, a mat is a dense biomass, so those toxins are present in high concentrations in the mats. Also, it seems that dogs are specifically attracted to the benthic mats and therefore may be exposed. And it's not only in Neuchâtel, it's in other Swiss lakes, it's in other countries that I've heard reports of dogs dying. And clearly you can imagine that there could be there could be risks, for instance, for children too. So this is a field of study where we don't know nearly as much as about the planktonic blooms. I think it's only New Zealand for now that has studied the risks of mats in depth, where they have guideline values for benthic cyanobacteria as well as for planktonic ones, but other countries are still developing this. And what is also different, like here for Neuchâtel, the mats actually, they grow in the river that leads into the lake. That's where the mats develop. And when they become detached, for instance, when they start to float with oxygen bubbles after photosynthesis, the mats may float into the lake and then be washed on the beaches where people are swimming and where dogs go into the water. But it's a different risk setting from the planktonic blooms where we know more. So we slowly come to the end of my presentation here. Just a few things about how do you reduce risks. This is a multi-pronged strategy. I think if you work with blooms, this doesn't come as a surprise. Lakes take their nutrients from the catchment. Risks go up with eutrophication, with phosphorus, nitrogen going into the lake. So you need to start treating the problem at the level of the catchment. You cannot separate the lake from its catchment when you think about blooms and the risks they pose, for instance, for recreation or for the production of drinking water. Start in the catchment, that's where you can really control the problem at its root, reducing nutrients. Of course, then there are things you can do in the water body. You can prevent water offtake from a site, for instance, from a depth where you have a deep chlorophyll maximum of Planctotrix. And of course, in the water treatment, you can even then remove cyanobacteria and remove their toxins. A similar message is portrayed here in these figures that come from a special issue in the journal Aquatic Ecology that we developed as part of the CyanoCost action a few years ago with Petra Visser, Jutta Passage, and Mayam Bormans as co-editors. And here we show that, like said just before, in order to prevent blooms in your lake, in your reservoir, you start with nutrient management in the catchment. Then you need to think about potentially treating nutrient loading at the inflow, as they do at some of the lakes in Berlin, where phosphorus is stripped right when the river flows into the lake. After years of eutrophication, even if you clean up the input, the external inflow, you need to be aware of phosphorus in the lake sediment and prevent internal eutrophication. And then at the top of this pyramid are all the things you can do in the lake, if you have blooms, you can control them, you can mitigate them by, for instance, artificial mixing, biomanipulation, flushing, or even you could think about treatment with hydrogen peroxide and others. Therefore, this multi-pronged approach that I talked about results to the notion of having multiple barriers to protect people against potential exposure to cyanobacterial toxins in their drinking water and other exposure routes like food. Actually, this notion of multiple barriers comes from food production. In food production, they speak about safety from farm to fork. So at every level in this food production chain, you should have barriers that prevent people from being exposed to toxic substances in their food. You can do something similar when it comes to drinking water. Here, the catchphrase would be from catchment to consumer, but again, barriers at every step to protect people from potential exposure to harmful substances in their drinking water. And that is explained in the book, and this is just a summary that you can take and read it in the book. So that brings me to my final slide. It's a slide I've shown before, I think even in GLEON, cyanobacteria as good, bad algae, blue-green algae. Why good? Clearly, they gave us oxygen in a way. It's the cyanobacteria that evolved the capacity to do oxygenic photosynthesis, and without them, without that invention, the evolution of complex life forms, including animals, would not have been possible. Bad, it's what we talked about today. They produce toxins, different groups of toxins, hepatotoxins, neurotoxins that clearly pose a risk when you're exposed to it through drinking water, through recreation, through food or renal dialysis and others. But maybe we have to say that in this second edition of the WHO book, we've sort of changed a little bit the way we look at the risks of cyanobacteria, that it's not always needed to take the lifetime exposure as the standard. Sometimes exposure, for instance, through seafood is more seasonal. Sometimes it's even just one-off event, and that leads to different guideline values. So the guideline values have become more diversified. The alert level frameworks take into account that depending on the things you measure in your local setting, you may keep a lake open for recreation. For instance, you may decide that drinking water, in particular with good treatment, can continue. It all requires local monitoring, local understanding to reach the conclusions that you feel safe with where you are, where you work. And that's what I wanted to say, and I'm happy to discuss with you in Gathertown later in the meeting. Thank you for your attention and hope to talk soon. Bye.